So now we are going to look at some specific architecture of neural networks, starting with the simple one, then move into more advanced models. And apparently there are some attributes you need to look after when you see a neural network structure. Like these are the questions you need to ask yourself. Number one is that the information simply flow from left to right, like which means is there any cycle or cyclic pattern inside it. If the information just goes from the input layer to the next layer to the next layer to the output layer, then we call this is a feed-forward neural network. Okay, information goes in a linear pattern. There's no going back of this information. Now, having said that, you will probably guess that there's some neural network that information can goes back. And as I mentioned earlier, there's a family called recurrent neural network that just does that. So information can flow back just to simulate the time factor inside it. So it's useful to do sequence models or to do some time factoring analysis. Okay, that's number one. Number two is that is the layer fully connected or densely connected. What it means by densely connected is that the neuron inside one layer is fully connected with the neuron in the next layer. So if you've got 3 neurons in this layer, 2 neurons in that layer, in the next layer, what we expect is there will be 6 connections between them. So if it follows that pattern, then we say it's fully connected or densely connected layers. They all mean the same thing, just different names. And in some programming interface, you will see dense layer that just means fully connected layers. Okay, so here is an example of a simple fully connected feed-forward neural network. So this is attribute number one, this is attribute number two, and this defines the structure of this neural network. Okay, it has an input layer which accepts information, and then information goes into the next layer, and then goes into the output layer. And now we're going to look at how are the information actually processed. So if you recall the perceptron, like when we talk about the history of neural network, it's very similar to that. The main difference is that instead of using the unit step function, we changed it to something that's differentiable. The reason we want all the stuff inside neural network to be differentiable is because when we use gradient descent, we want to find those gradients. If it's like a unit step function around these areas, it's not differentiable because the slope in this region is infinity, which will cause the optimizer to fail. Okay, anyway, let's look at this. So information on all these neurons in the input layer will get into this neuron. So we focus on this part. So Z is just a linear combination of all the input plus some bias. So these are called the weights. These are called weights, and the intercept is called the bias. Okay, there's a famous tool called weights and biases to manage parameters if you want to chain multiple architectures or run multiple experiments. So that name comes from here, weights and biases. They just mean slopes and intercept if you're thinking like a linear regression sort of way. Okay, so information gets sum, so it's weighted sum of all the input, and then it's going to pass into a function called activation function. So the reason we pass this activation function is something I explained earlier. We want something that's nonlinear so that we can learn more complicated pattern. So if a neural network like this, information goes in, this is a linear combination of all the inputs here, and then this one is a linear combination of all the inputs here, then making the neural network deep doesn't have any meaning because at the end you can express like the output on this neuron as a linear combination of the original input, right? So the reason that deep can make sense is because there's some nonlinearity in each of these modules so that it can make the learning more complicated. Okay, so that function is called the activation function. And if you call the perceptron, that unit step function can be thought as that early age activation function. And this nonlinear function is very important, and this is something that you need to choose when you design a neural network. Okay, so now what we do is that we have that linear combination but pass into this activation function, and that becomes the output of this neuron. So this neuron will pass information further into further neurons. So this is the number A output of this neuron. And as you can tell, this is like a stack of perceptron. So this is exactly a multi-layer perceptron using a activation function of your choice. So then comes to the question, what activation function can you choose? Well, the most commonly used are the sigmoid function. And if you recall from the last lecture, we have logistic regression which map like a range of minus infinity to the range of 0 and 1, so that we can interpret, say, if the prediction is 0.8, we can sort of interpret that 0.8 is the likelihood that the sample is classified as number 1. Okay, so it has some meaning to that. However, here the main reason we use the sigmoid function as the activation function is to use the property of the non-linearity of this function. It's a nice S-shaped function like this here. Okay. Sometimes what you see is there's another parameter in like before x, so you can further control, does it like go up quite slowly or go up quite significantly and sharp. But in all the cases, this is differentiable, and this is the key difference from the unit step function. Okay, and then we will have more commonly used nowadays the ReLU function, which stands for rectified linear unit. The reason is that when we calculate the gradient of this one, it will be quite different at different x positions, which means the gradient is a function of x. But when we calculate the gradient of this ReLU, it will be quite simple. If it's zero, if it's below zero, then it's zero. If it's above zero, then it will be 1 in this case. Okay, so for now, what you need to know is that a neural network is just like the multi-layer perceptron. A fully connected neural network, what we just look at, is just like a multi-layer perceptron, but we use a differentiable activation function instead of a unit step function. Now, getting back to this slide, sometimes you are asked to calculate how many parameters are there, because the parameters are sort of the degree of freedom inside the model. And if you have a larger set of parameters, which means your model can learn more complicated pattern. So this is sort of like the brain size or the brain volume of a species. Now, we humans have quite large brain volume. You can think of that's a large neural network with lots of weights and biases inside that. While in other animals, it might have less or even bigger brain sizes. So that makes things a little bit different. Now, thinking about this neural network here, if we got M neuron here and we have N neuron in the next layer, it will be quite simple to calculate all the weights, because it will be just M times N. That's the number of weights. So basically, each connection here will have a weight that's used to weight the input that will go pass into the next neuron. Okay, and also for all the receiving neurons, there will be a bias, which means the bias number will be N. So the total trainable parameter number is equal to M times N plus N, which means it will equal to M plus 1 times N. Okay, so this is how you calculate the total number of chainable parameters for a feed-forward fully connected neural network. Now, this only works for this type of neural network because it's fully connected. And if you try to work on, say, the convolutional layer, then the calculation is different from this. Okay.